All right, so last time we saw how we can use the sigma notation and the Riemann integral to actually find the area under a curve. And I mentioned earlier that we will be able to use the antiderivative uh, to figure out area as well. Before we could begin to run, however, we have to again walk and crawl. So in the past lecture we were crawling, now we are actually beginning to walk. So first of all, we're going to be talking about this definite integral. Now, in short and very informally, what the definite integral allows you to do is that if you have a function like f of x dx, you find the integral of that, we know that this has an antiderivative f of x plus c. That's what the antiderivative of x is. And I mentioned that finding out what this c value is, it's actually very important, and there is a way of doing it. And to do it, we use the definite integral. So the definite integral will give us the solution to this value of c, and it will also give us some more information about um, what the integral is representing. So first of all, let me define what the definite integral is. Now, for those of you who are going on to take calculus 2, much like the antiderivative, the definite integral is probably what you'll spend 90% of calculus 2 in. Well, I'll say 85% of it. It's definitely spent on learning about how to solve definite integrals. Obviously, solving definite integrals involve taking derivatives. Now, the definition is as follows. If f is defined on the closed interval AB, and the limit of Riemann sums over partitions delta, it's the following limit over, this is called the norm, and the norm represents the largest subinterval of a partition. So that's called the norm. So if the limit of the norm, as the norm goes to 0, of this sum, I equals 1 to n for f of ci delta xi. I remember here ci is the same thing as xk that I had prior. It's just notation wise, so they're the same actual thing. Anyway, so if this limit exists as described above, then f is said to be integrable. Integrable on the closed interval AB, and the limit is denoted by the following. Limit as the norm of delta x goes to 0 of the sum of from I equals 1 to n of f of ci times delta xi is equal to the definite integral from a to b of f of x dx. Now this limit is called the definite integral of f from a to b. Now the number a and the number b, well, the number a is what we call the lower limit, of integration, and the number b is the upper limit of integration. So when somebody says, what are the limits of integration of an integral that you're given, you know that the limits of integration are a and b. Now, this is very similar to the notation that we use for the indefinite integral. Now, when we go into the fundamental theorem of calculus, which is going to come in the next section, we will go into why this is the case. Now, for now, it is important to see that the definite integral and the indefinite integral are two different concepts. Okay, they're not the same. A definite integral is going to give us a number, where an indefinite integral is going to give us functions. Okay, as I wrote up here, when we have the indefinite integral, we get functions. This is a family of functions because that c could be any number. When we actually get a definite integral, we're going to get a number. We're going to get a limiting process. Remember that the limit, when it exists, is going to be equal to some number L, right? So because this is a limiting process, we're going to get a number as a solution. Okay? Now, there's another theorem that you should definitely know. If a function f is continuous on the closed interval ab, then f is integrable on ab. What that means is that the definite integrals exist. The definite integral from a to b of f of x dx exists. Now you may say, well, that's obvious, but it actually isn't that obvious, because if you look back at the definition of the definite integral, f is defined on the closed interval ab, but there's no mention of f actually having to be continuous up here. It's just a mention of this limit existing on that interval. Okay? Now this is guaranteeing us that if we are given a function that is continuous on some closed interval, then we are guaranteed that that function is integrable on that interval. Okay? And we know that this definite integral actually exists. Now, for the following, so let's do an example. So for example, let's evaluate the definite integral using this definition. At this time, this is the only way for us to actually find or solve the integral. So evaluate the definite integral. From minus 2 to 1 of 2x dx. Now, 2x, if we graph it, it's just the equation of a line and goes up from left to right. Right? We have 0 here. At x equals 1, we have 2. At x equals 2, we have 4. And so on. At negative 1, we have negative 2. And so on. Now, if we were to look at the definite integral, if we were to look at the area underneath the curve with relationship to the x-axis, this is what it will look like. It will look like, we have a bunch of rectangles, again by the Riemann integral, that we're going to be adding together infinitely many times, and this is going to give us the value of the integral. Okay. Again, this is in relationship to the x-axis, so that's why we also have these rectangles going in the other way, in the other directions. Now, because this function is continuous on this on the entire number line, then if we pick the closed interval, like the closed interval negative 2 to 1, it should be somewhere like here, negative 2 to 1, so this interval right here, then this function is integrable on this interval. So because 2x is continuous on -2, 1, f of x equals 2x is integrable on this interval by the theorem. That we are guaranteed because it's continuous on a closed interval. Now, the definition of integrability means that for any partition whose norm, meaning whose biggest partition approaches 0, we can use it to find the limit. So we are going to be subdividing this interval into equal pieces. Now, this is something that I didn't mention in the previous lecture, but I should mention as an aside because it's important. We can make subdivisions of intervals with unequal width. So you could actually make rectangles that have different width sizes and add them up together and get the area. That is also possible. We're not going to get too much into it because for the most part we will only be dealing with subintervals that have equal width. Now, if we take this subinterval from -2 to 1 for our function f of x equals 2x, and we divided this delta x into subdivisions of the interval that are equal, then what we will have is, again, b minus a over n. Now, again, we don't know how many partitions we're going to make. That's what n is here for. But we do know what b is. We do know what 1 is. So we have 1 minus -2 divided by n. And it's could be increasing up to infinity depending on how many subdivisions we pick. And it could be 1, 2, 3, all the way to infinity. So, but with this we could simplify. This is 1 plus 2 over n, which is 3 over n. Minus and minus is plus. So notice that now we have the width of our rectangles. It's 3 divided by n. Now, if we use the right endpoint, so I'm basically using a Riemann sum to evaluate this. If we use the right endpoint, we have, remember, xk is equal to a plus k delta x. So we have xk is equal to a. Well, what is a? A is 1 plus k, and delta x is 3 over n, so k times 3 over n. So that is what our right endpoints are equal to. Now, why are we focusing on these right endpoints? We're focusing on the right endpoints because by definition of the definite integral, we can use a Riemann sum and take the limit of the Riemann sum to find out the value of this definite integral. So we have found delta x, we have found the ci or xk, so it's just a matter of now plugging in and taking the limit. If we are able to plug in into this Riemann sum and solve, then we will be able to find what the value of the integral is. So what we have is that the definite integral from -2 to 1 of 2x dx by definition is equal to the limit, so the norm of delta x goes to 0, of the sum from, I'll actually use k here. K equals 1 to n, just to be consistent, of f of xk times delta x. That's what we have. Now, what is that equal to? Well, that is equal to the limit as n goes to infinity. And as n goes to infinity. Yes, n going to infinity. All right. N goes to infinity. Of k equals 1 to n of f of xk times delta x. Now, the reason why we're doing this is because we know that our subdivisions are all of equal size. So that's why we're doing this. Our subdivisions are all of equal size. So they're going to infinity because we are increasing the number of subdivisions that we're using. Okay? So what do we have here? Well, we could substitute now. So we have limit, n goes to infinity of the sum of k equals 1 to n of f of 1 plus k times 3 over n, that's from up here, times delta x, which was 3 over n. Okay. Oh, I picked actually the wrong a. A was -2, not 1. So this is -2. My apologies. -2. So used to the bigger number being the a. All right, so what do we have here? Well, what was f? F, if you remember, which you probably don't, f was equal to 2x. That's the value given right here. So if I'm evaluating f of -2 plus k over 3n, then what I really have is the limit as n goes to infinity of the sum of k equals 1 to n of 2 times what the input is. The input is -2 plus 3k over n times 3 over n. All right. But now, what can I do? Well, first of all, I'm going to multiply 2 times 3. Basically, this 2 times this 3 over n. And that's going to give me the following. That's going to give me equals 1 to n of 6 over n times -2 plus 3k over n. Okay, so I just multiply this 2 times this 3 over n. Now notice that this sum is with respect to k. So because the 6 over n has no k value, we could treat it as a constant and actually pull it out. So this is limit as n goes to infinity. If you take out the 6 over n times the sum of k equals 1 to n of -2 plus 3k over n. This is all using the definition. And now, let me give myself some more space. We have limit as n goes to infinity of 6 over n. And what we're going to do here is, you see this sum, we're going to use the rules that we had in lecture 22, part 1 to solve this. So we're going to first break it up because we have a sum here. So we're going to break this up as the sum of k equals 1 to n of -2 plus the sum of k equals 1 to n of 3k over n. And now we're going to use the constant multiple rule for the first one, and then we're going to pull out the 3 over n on the second one, and you'll see that we will actually know a sum in terms of n for this one. We know what the result is equal to. Anyway, this is equal to the limit as n goes to infinity of 6 over n times what? Well, we pull out that -2, and we have the sum k equals 1 to the n of blank. I mean, I could have left the 2 there, but and I could pull it out as well. Technically, I have a 1 there. Plus the sum, again, I'm pulling out this 3 over n on the outside, of k equals 1 to the n of k. But if you recall from lecture 22 part 1, we know that the sum k equals 1 to n of cn of c is equal to cn. That means that this piece right here is just going to be equal to n because c is 1. And we know that the sum of k equals 1 to n of k is equal to n times n plus 1 over 2. That is one of the formulas that I gave you in the previous lecture. So I'm just using things that we have seen before. This is not magic. It's not popping out of thin air. Well, what is this equal to? Well, we have limit n goes to infinity of 6 over n times minus 2 times what I just said. This is, for this particular one, it's just n plus 3 over n, and then this whole thing becomes n times n plus 1 divided by 2. Okay, and we're finally almost done with this problem, and this is using the definition. So if you were asked, which only for the homework you'll be asked for this in one problem, not even like the whole homework. For the exam, the final exam, you don't have to use the definition. We're gonna get a technique that will oversimplify this to the point that this becomes better. But again, before we can run, we have to learn how to walk. So using the definition, we have to go through all of these hoops and valleys. Anyway, so let's simplify. Everything now is in terms of n, and we're taking a limit as n goes to infinity. So this actually doesn't, it's not looking too bad anymore, because this is something that we've been doing since day one of this class. So again, limit as n goes to infinity of 6 over n, and then we have negative 2n plus, and now here you could cancel out the n's, so long as n is not equal to 0. So we have 3 times n plus 1 over 2. So this is equal to the limit as n goes to infinity of 6 over n times minus 2n plus 3n plus 3 over 2. And now we could combine fractions and then multiply and take the limit. So we have, if we combine these fractions, this is missing a 2, so this is 2, and this is going to become a 4. Just basically multiplying by 2 on both sides, so it's going to be minus 4n over 2 plus 3n plus 3 over 2. So we're going to have limit as n goes to infinity of 6 over n, and then when we combine it, 3n minus 4n is negative n plus 3 divided by 2. And now, let's see what we get. Oh boy, I think I made a mistake. I hope not. Let's see. Yeah, I did. Let's see. Yeah, I definitely made a mistake. My mistake is right here. Sorry about that. I actually cannot cancel that because I have division there, and this is going to be a binomial, so I cannot just cancel it right away. So I mean that this is wrong, and this is wrong, and this is wrong, and this. So what we really have here, let's first multiply, so that we got to be careful here. This is n squared plus n divided by 2. There we go. So now you can see that we're going to get here 1n cancels with this, so you get 3n over 2 plus 3 over 2. That's what we get here, because you multiply the 3 into it, so you get 3n squared plus 3n, and then when you divide by n, they cancel out, and you still have the 2 there for each of them. Oh boy, that was a close one. All right, so now what we really have is 4n over 2 plus 3n over 2 plus 3 over 2. So now we could combine all of this. Oof. Thankfully we got all of that. So this is equal to what? This is equal to negative n plus 3 over 2. Actually, I think it was probably the same answer, but it's better to be safe than sorry. And what is it equal to? So this is going to be equal to limit as n goes to infinity. You multiply the 6 into it, and then the 4, and then the n. So it's going to be negative 6n plus 18 divided by 2n. And now we can actually take the limit. So if we take the limit as n goes to infinity, so limit as n goes to infinity, remember the degree of the top and bottom are equal, and we learned that when this is the case, then the limit is going to be equal to the ratio of leading coefficients. So what we really have here is -3. If you want to see it slower, what's going on here is limit as n goes to infinity of -6n over 2n plus limit as n goes to infinity of 18 over 2n. Now this limit is going to be equal to 0, and this limit is going to be, the ends cancel out, so you just get -3. So the limit is equal to -3. Okay, so that is the end of this problem. So we have that the integral from -2 to 1 of 2x dx is equal to -3 by using the definition. Notice that this was a very long and very tedious process. In the next lecture, we're going to actually get a tool that will allow us to do this much faster in the fundamental theorem of calculus. Now notice that this definite integral is negative. So note, this definite integral is negative. In fact, the definite integral can be positive, negative, or 0. So this is something that is good to know. Now, since our answer for the integral of -2 to the 1 of 2x dx is equal to -3 and is negative, it does not represent the area under the curve or under the graph of 2x, because area is positive. So it turns out that for the definite integral to interpret area, it must be it must be defined under a non-negative interval. So for the definite integral to be interpreted as area, the function must be non-negative over an interval. Must be non-negative over a closed interval. So let me write down that theorem. So it's a very important one as well. So again, if f is continuous and non-negative on the closed interval AB, so this is formally AB, then the area of the region bounded by the graph of f, the x-axis, and the vertical line of the endpoints x equals a and x equals b is given by the definite integral from a to b of f of x dx. This is what area is defined to be in terms of the integral, of the definite integral. So for the definite integral to represent area, f must be continuous, non-negative on a closed interval AB. Okay. We will be using this more again in the following section when we actually get to use the fundamental theorem of calculus. At this time, the um, the tools that we have will make our work very tedious if we had to compute this by hand. As you saw in the previous example, it takes forever to do a problem like this using the definition. Now, it turns out that we can solve some basic areas. So, for example, let's say somebody gives you the following integral. Like right now, we could solve these areas because they represent geometric figures, like the integral of from 1 over 3 of 4 dx. Well, the function here is f of x equal to 4. That's what the function is. F of x equal to 4 is the same thing as y equal to 4. And y equal to 4 is a horizontal line. That goes like this. It's a horizontal line. Now the interval goes from 1 to 3. So I have 1 here and 3 here. So the vertical lines of x equals a and x equals b are this one, and the x-axis is here. So we are talking about this area. Notice that this area is a rectangle. The base is 2. We know the height is 4 because it goes from 0 to 4. So we can actually compute this area without having to use the definition of the definite integral, because this is just represents the area of a rectangle, which is base times the height. So notice this is the area of a rectangle, which means that we just have 4 times 2, which is 8. So this area is 8. So if somebody comes up to you in the street and gives you a definite integral, like the definite integral from 2 to 5 of 8, then you know that that represents the area of a rectangle. Okay? Let's do another one. What about the following? What about somebody comes up to you and gives you the integral from 0 to 3 of x plus 2 dx. Now here the function is equal to x plus 2. If you graph this, you see that it has a y-intercept at 2. This goes from 0 to 3. So we don't care about anything on the left side of it. We only care about things on the right side. We know it ends at 3. We can actually find out what the value of 3 is, because 3, if you plug in 3 for x, you get 5. So it actually goes higher to 5 up here. So these are our endpoints. So this looks like this. Goes up, down here, up here, and up here. And this shape is the shape of a trapezoid. It turns out that the area of a trapezoid, if you don't remember from, I think, 7th grade math, which I don't suspect that you do, is given by 1/2 times the height times base 1 plus base 2. Okay, so here I have a trapezoid. The height is actually given by this piece right here. That's the height. Base 1 is this distance right here, and base 2 is this distance right here. So we have that this integral, this definite integral of x plus 2 dx, is actually equal to the area of a trapezoid, and by what I just wrote, is 1/2 the height times b1 plus b2, base 1 plus base 2, which is 1/2. The height here is 3 because you go from 0 to 3. Base 1 is 2 because you go from 0 to 2. And the other one is 5 because you go from 0 to 5. So 0 plus 2 plus 5. And when you multiply all of this together, you get, 2 plus 5 is 7. 7 times 3 is 21. So you get 21 over 2. So we got that this area of this trapezoid is 21 over 2. And notice that I didn't have to use the definition of the definite integral. I didn't have to do all of this work. I certainly could have. It is possible to do all of this, obviously, by using the definition. You will just have to, find the width of your rectangles, find the height, and so on, and then use the definition to take the limit. But that will take us forever, like the example that I did, which did take us forever. Let's say somebody comes up to you and gives you the following. Let's say they give you, they give you the following: the definite integral from -2 to 2 of the square root of 4 minus x squared dx. Now, for the untrained eye, this will look like this is a radical function, but when you see something like this, you should know that this is the equation of a semicircle. Okay, this is the equation of a semicircle, center at 0, center at the origin, that goes from 2 to -2, and it is the upper half, because it's positive, of this circle of radius 2. Okay, if you don't believe me, simply write it: y equals radical 4 minus x squared, and then remove the square root. You square both sides, right? You get y squared equals to 4 minus x squared. Then move the x squared to the other side, and you get y squared plus x squared equals to 4, and that's the equation of a circle. I mean, you could write it as this: y plus k squared plus x plus h squared equals to r squared, and then you'll see that it is in fact the equation of a circle. In this case, the half circle, the semicircle, the top half of the circle. In any case, we know that the area of a circle is given by pi r squared, and because this is half the circle, then the area of a semicircle is equal to 1/2 pi r squared. So we could calculate that the definite integral of 4 minus x squared dx is simply equal to 1/2 pi, and r, we know that the radius is 2 squared. Well, this is the same thing as 4 pi over 2, which is the same thing as 2 pi. So we get that the area of the top part of the semicircle is 2 pi. So using simple geometric figures, we can actually solve this definite integrals, because they do correspond to some geometric shape. So that is something that you certainly need to know. Certainly.